Okay, page 20 of the scheduling notes. This is section 6.3 and it is called rate monotonic or RM scheduling. And the text reference for this is 742. Okay, so rate monotonic scheduling is not another runtime scheduling technique like fixed priority or EDF. It is a way to map deadlines to priorities. Maps deadlines to priorities for fixed priority preemptive scheduling. So the runtime scheduler will be FPP, but you do this mapping ahead of time, and the fixed priority is inversely proportional to the period of the task. The task with the shortest period will have the highest priority. The task with the longest period will have the lowest priority. And in real-time systems, especially safety-critical systems, it's important to be able to prove analytically that your task set is schedulable, meaning that it won't miss any deadlines. So a lot of effort is put into devising these schedulability tests. And this test can be done beforehand, but it can also be performed at runtime to decide whether to admit a new task, a newly created task, to the task set. So the given task set is schedulable. I think my spell checker usually doesn't like that word, but it's a real word, at least in the scheduling literature. It's schedulable by RM if the product for I equals 1 to n of all the tasks of 1 plus the task processor utilization, so CI over TI, is less than or equal to 2. And let's just add a note here that schedulable in this case means won't miss a deadline. And so you can compute this beforehand when you're creating your application, but some applications require you to add new tasks as the application runs. And if you already have this product stored, then it's easy to multiply the product times 1 plus that utilization. And you can do that in order one time. Let's look at an example. So we've got the period and the worst case execution time, and let's just say that our task set has 3 tasks with periods 10, 12, and 6, and worst case execution times of 2, 3, and 1. And just a reminder that the assumption that we're always using is that the relative deadline is equal to the period. So it's due, once a task is released to run, it needs to finish before it's released again for another run. So step 1 in this case would be to check the processor utilization of the task set. So that's U equals 2 over 10 plus 3 over 12 plus 1 over 6, and that's roughly equal to 0.62, and that is less than or equal to 1. So that's good. Step 2 is the schedulability test. And so we take that product, which is going to be 1 plus 2 over 10 times 1 plus 3 over 12 times 1 plus 1 over 6, and that is equal exactly to 1.75. And the schedulability test up at the top here was that it has to be less than or equal to 2. So that is less than or equal to 2. And so this task set is schedulable using rate monotonic to assign fixed priorities. And I just want to make one point to go back up here. The task set is schedulable by rate monotonic if. That's not if and only if. So what that means is, if this condition is true, then yes, the task set is schedulable. But it doesn't mean the reverse. It doesn't mean that if the task set is schedulable that this inequality will be satisfied. So what that really means is that there can be some task sets that are actually schedulable but will be rejected by this analysis. This analysis was developed or published in 2003. Before that, we were using an older analysis that was developed, or a test that was developed in 69 or 70, and it had an upper bound on processor utilization of 69%. This does much better. In the worst case, when the processor utilization is evenly balanced between your tasks, then it will approach that bound of 69%. But in most cases, it does better than that. And in the best case, where the distribution of work between the tasks is really unbalanced, it will approach 100% processor utilization.